All right, so we looked at a situation when we had two variables and they were related row by row, so we were able to subtract them and find the difference. So looking at that in the spreadsheet again, we had the organic effect, and we looked at organic, non-organic minus organic, and we could boil it down to a single variable. Can't always do that. So I'm going to grab this data from StatKey about mindset matters data set, weight change by whether they were informed or not. And I'm going to bring that into a spreadsheet to analyze. So there's the inference examples chapter 6 spreadsheet that I gave you, and you want to scroll along the bottom to look for two mean hypothesis test, one where we can play with the data. So we have two different columns, and I'm going to switch from that one to my personal one. All right. Two mean hypothesis test. All right, so I'm going to delete the data that's there. And then I've got a little manipulation I got to do off to the side before. All right, so I need to separate these and get them into a way the spreadsheet can handle them. Let's see, we're going to split them. Beautiful. Okay, so I'm going to take the nose. All right, so this is the weight change for the nose, and again, we'll double check these values. Let's copy them out. So we'll call these uninformed. Oops, I could spell right. Again. All right, and then we have the ones that were informed, that their work was active and healthy. So those are the yeses down here. All right, so these numbers next. And then we have to confirm about the order in which those numbers were created. So what these numbers should be, let's make a note about them here. This is weight change. And I'm pretty sure that was in pounds, but we'll go look at the data set to make sure. All right, so done with that for the moment. Let's get the description here. Here, third edition, dataset description. All right. All right, here we go. All right, so we have weight, their original weight, and then we have their weight later. So the weight change is the difference. So probably their new weight, weight 2 minus weight 1. All right, let's confirm that. Here's the Mindset Matters original data set. Weight change, I got that over here. So if we take weight 2 minus weight 1, then we should have a 0.4. Make sure the order I did that. Yeah, weight 2 minus weight 1. And so for the zeros, those would be the nose, the uninformed. We should find the mean there. Negative 0.2. All right, spreadsheet says the mean there is negative 0.2. Okay, and then the mean weight change for the others was much higher, negative 1.878, blah, blah, blah. All right, let's don't need that many decimals there. Probably 2 decimals is sufficient. Okay, so in this case, it would be inappropriate now to subtract these two numbers because those are two different people, right? They're unrelated. Whereas in the Mindset Matters data set, when we're looking at, say, just this right here, we can't subtract these two numbers because that's the same person right there and right there. So we always have to ask ourselves, is this data paired in such a way I can do subtraction or not? If not, then it's two different groups that we're comparing, and we have to run the appropriate hypothesis test. And again, you'll notice that in StatKey, they distinguish between running a hypothesis test for a single mean or testing for a difference in means. So that's two different groups, you're comparing their averages. That's what we're doing here. Formula for that is a little more complicated. So let's jump over here. So I have a difference in means. And my sample statistic is a combination of statistics. And so often you'll see it something like x bar 2 minus x bar 1 for the sample statistic. And here I should note my x bar 2 is the weight change of the uninformed maids and 1 is the weight change of the informed maids. And our parameters have the same description. So the parameter, the population parameter of interest here, that would be mu2 minus mu1. And again, these are again sample values, and we're using samples to estimate the population. So for example, the weight change for the informed maids, the ones that knew their work was active and healthy, was negative 1.78 pounds. So then we would predict that any group of maids who were told their work is active and healthy, then 4 weeks later we would expect them to lose about 1.78 pounds. And the weight change of the uninformed ones, we would expect about no weight change. Remember, that one was about negative 0.2, so minor change there. So if we run a confidence interval on that, 0 is definitely in the interval there. 0 might not be in the interval on this one here, but that's a whole other question to ask. So many questions, so little time. And again, what is the description of mu2? Well, that would be the weight change of all uninformed maids, maybe in New York. So again, outside of this sample, where did these 75 people come from? So I'm just elaborating on what uninformed means. Healthy, there we go. And B1 would be the same thing, but they know. And continue. Similar sentence. So rather than write the sentence, I'm just going to move on to the actual hypothesis test. Let's see, next page, let's draw what this is going to look like. As usual, we're going to draw a normal distribution. Oh, I should state my hypotheses, shouldn't I? In the middle goes mu2 minus mu1. And we believe there to be no difference in the two groups, that the weight change in the two groups is the same. Now in the samples we can clearly see it's clearly not the same, but they might be like, close enough that no big deal. Okay, now what am I going to assume here? I'm taking, what is my hypothesis? mu2 is the uninformed maze. So if I subtract one from the other, x bar 2 minus x bar 1, that's going to be negative 0.2 minus negative 1.78. That's going to give me a positive difference of 1.58. So that means the informed maids on average lost more weight. Okay. So I'm going to take my hypotheses to be null hypothesis, no difference in average weight change, so mu2 equals mu1, and then my alternative hypothesis is that mu2 is greater than mu1. So that means I'm going to do a right tail test. So then my difference is going to be somewhere out here. Now, again, about 1 standard deviation, 2 standard deviations, 3 standard deviations. I don't know how far it is till I calculate what a standard error is. So that's where the spreadsheet helps. So off to the spreadsheet to figure out how many we got. This one. All right, so we have the 2 data sets in there. And when we subtract them, we get 1.59. Okay, so it was close, a little bit off there. So that's our sample statistic. That leads to a standardized test statistic down here. Standardized test statistic, which tells us how many standard deviations that is from the expected null hypothesis, which is no difference. And it says it's going to be about 2.6 standard deviations away. So if I look at my graph, again, this is 1 standard deviation, 2 standard deviations, 3 standard deviations. I'm 2.6 standard deviations, so my test statistic falls about here. X bar 2 minus X bar 1. And my p-value is however many samples end up in that region as a proportion. And I didn't look at that. Let's see what my p-value is. P-value for a right tail test is 0.0063. Well, that's a pretty small p-value. That is definitely less than the standard significance level alpha of 5%. Which would be 0.05. So that leads me to decide to reject the null hypothesis and accept the alternative. I have data to support it. And hypotheses are all pretty similar. Stating the conclusion, you would state, in this case, I do have significant evidence that there is a significant difference, and then go state what the difference is. So let's give that a shot. So we have sufficient evidence that, let's see, a couple ways I could state that. I could just state that there is a, let's see, there's not only a significant difference, we did a 1-tail test, even a 2-tail test, we would still have significance. I don't want to word it, that's always the hard part. Average weight change of uninformed maids. Is greater, but the weight change being negative. Okay, I know how to word it. Okay, so we have sufficient evidence that the average weight change maids who know their work is active and healthy. It's more than those who don't know. That's the essence of what we just showed here. And again, this is a tricky one because we had differences and averages to look at. It's a little more complicated than looking at just a single variable. All right, so next thing I'm going to do just to back this up is I'm going to compare what StatKey thinks about the theoretical calculations from the central limit theorem. Right, so I am using a t-distribution to calculate this particular p-value. And to do that, I had to do a whole bunch of calculations, right? I started with the raw data. I had to then count, get their means and standard deviations. Based on that, I had to find the difference in means, the degrees of freedom, the standard error, the t-score, and then finally I could get that p-value. Right, so there's this whole chain of calculations that have to happen. Now, StatKey is similarly complicated, but it does it with randomization. So here's that data set here. And again, let's see if StatKey subtracted them in a different order than me. Nope, same order. They just labeled them different as 1 and 2. That's okay. But we're still going to run a right tail test. So once I have the right data and the hypothesis, then I generate at least 5,000. I'm looking for the standard error to settle down. Standard error settled down there. And 0.643 should match about the standard error we saw over here. Ballpark, close enough. Where'd you go? There you are. And then I want to do a right tail test. And then I have to enter the actual sample statistic, 1.59. And I should get a similar p-value. 0.0065. We had 0.0063. Pretty damn close. All right, so StatKey verifies through a randomization test. Which should I use? Should I use the central limit theorem or should I use a randomization test? Well, since the sample sizes are each above 30, I can use the central limit theorem. You can always use a randomization test. So I can use both in this case. All right, that's it for now. Take care, do good math.